This is part 2 of the NMR interpretation tutorial. In part 1, we discussed the interpretation of proton and carbon 1D spectra, and in this demonstration I would like to describe the use of two-dimensional techniques, in particular the heteronuclear correlation experiment between proton spectra and carbon spectra. We are looking at ethyl crotonate, which I've drawn right here, and I'm using a labeling scheme where the carbons are labeled A, B, C, D, E, F, and the hydrogens are labeled based on the carbon that they're attached to. So this is hydrogen HA, and there are 3 of them, and I've just labeled them numerically A1, 2, 3. And I've written down in the lower left-hand corner here the preliminary assignments that we made based on the one-dimensional spectrum. The two-dimensional heteronuclear correlation experiment tells us something about the communication between the protons in the molecule and the carbons in the molecule. In this particular experiment, the proton spectrum is on the x-axis, and the carbon spectrum is on the y-axis. Let's take a look at the signals that show up at the high field end of the proton spectrum. So we've got a triplet at 1.2 roughly, and we've got a doublet of doublets at approximately 1.8. The heteronuclear correlation spectroscopy tells us that the triplet is interacting with the carbon that shows up at 14 parts per million shift. Now, if we take a look at the molecule here, in the previous example, we learned that CH3 saturated carbons typically show up in the region of around 10 to 50 parts per million, and the spectra are influenced by electronegativity effects. Originally what I had said was that the carbon A, since it is close to the oxygen here, that carbon A would be affected by a downfield shift due to the oxygen, and therefore carbon A would be the peak that shows up at 17. However, the heteronuclear correlation spectroscopy tells us that this is not the case. The triplet clearly is this part of the molecule, and the cross peak here shows us that this peak is actually 14 parts per million. So far, I'm 0 for 1 in the interpretation of the carbon spectrum. Actually, I'll be 0 for 2 because that means that if I got that one wrong, then I also got this one here wrong. Let's see if I can do better with the next one. We zoom in to this region here. Originally I said the proton feature at 4.1 is due to B. Let me click that. So that's this CH2 group here, and we would expect that to show up in a region that is around 50 or so, 50 to 70 parts per million, due primarily to the presence of the electronegative atom. I therefore assigned carbon B to the peak at 60 parts per million. Heteronuclear spectroscopy, the 2D experiment, confirms that. Yay, got that one right. We'll skip C for a minute, and we'll jump down to this region where we have the 2 CH groups. So we're talking about this region of the molecule. And originally I said that carbon D, so proton D, shows up at 5.8, so that's this one right here. And I said that it would be correlated to the carbon at 144. Uh-oh, looks like I made a mistake again. It looks here that the proton at 5.8 is actually correlated to the signal that's at 123, and therefore the proton at 6.9 is correlated to the carbon at 144 parts per million. So now I'm in a little bit of a bind. I don't know if my carbon interpretation was wrong or my proton interpretation was wrong. Let's take a closer look at the carbon spectrum, or sorry, the proton spectrum one more time, paying close attention to the coupling constants. So for part D, for hydrogen D, which I said was at 5.8 parts per million, we see coupling constant. First we see a doublet of quartets, and one coupling constant has a value of 15 hertz, and the other has a coupling constant of just around 2 hertz. That's consistent with coupling to a trans hydrogen across the double bond. That's a 15 hertz coupling constant. And the 2 hertz is consistent with long range, so a J4 coupling, 1, 2, 3, 4. So that's a J4 coupling with, say, for example, these atoms here. So I'm confident at this point that my hydrogen assignment is correct. Let's take a quick look at the other feature at 6.9. But before we do that, let's predict what we would expect to see. I'm claiming that this hydrogen shows up at 6.9. So we should expect a coupling constant of around 15 hertz, which gives us the trans across the double bond. And then the big difference, however, is going to be the coupling with the F hydrogens, because that is now just a J3 instead of a J4. So that I would expect to see coupling constant closer to 7 hertz. Let's see if I'm right there. We zoom in, and we see 7 hertz for the quartet, and we see 15 hertz to making the doublet. So that tells me that I can have a fair amount of confidence in my assignments of proton D and protons in E, which means that my carbon spectrum interpretation leaves a little bit to be desired. So let's go back to the 2D heteronuclear correlation experiment just to make sure that we are fully understanding the spectrum. We said that the peak at the proton signal at 5.8 is due to our D hydrogens. There we go. Therefore, carbon D is showing up at 123 parts per million. Great. That means that carbon E must be showing up at 144, since it is the one that should be correlated to the signal, to the proton signal at 6.9. And that is what we see. Great. So we are, I'm comfortable with my interpretations. Notice how there are only 1, 2, 3, 4, 5 signals in the heteronuclear correlation spectroscopy, whereas there are 6 carbons in my spectrum, or in my molecule. Carbon C, because it is not connected to any hydrogens, is not going to be correlated to any hydrogens. So this experiment tells us nothing about that particular carbon, and we're left with relying on the carbon-13 spectrum to determine that the identity of that carbon. The take-home message here is that we are going to make some mistakes or some misinterpretations if we rely on just one set of experiments. And it is important that we take advantage of all of the NMR spectroscopy tools at our disposal to make sure that our assignment is consistent with all of the data.